Time we stopped at during proof of a certain proposition. So let me remind formulation of the proposition itself. So this was a proposition about existence of a lift with respect to some given covering P. And we want to find the lift of a function from y times interval to x. So this is some given function f. And moreover, we have fixed restriction of this function at y times the beginning of the interval, and we have a fixed lift of this restriction f0 tilde, and we are wondering about existence of the f itself. And the statement is that for fixed p f f0 tilde, there exists unique lift. And the lift, by definition, is such a function, so this diagram commutes. You can go either this way or directly with this, and the result is the same. Okay, so so we started the proof. There was this was an interval, and this was our space y, and it mapped space x, and there was some x tilde. So what we did, we chose a certain point in y times interval, which we denoted by y0 t, and then it mapped something to f y0 t. And since f is continuous, for any such point, there exists a neighborhood let's NC. So actually one can, without loss of generality, one can assume that this the neighborhood is of this form. So let me. So last time I think I wrote open brackets, but actually without. I mean, it's a bit easier to show use the close bracket, and we can actually assume this without loss of generality that this is neighborhood of this form. So it contains y0 t such that the image of this neighborhood is contained in open set U, which is evenly covered. Okay, and why is that? This is because so since so if you choose U, then it's open. So first of all, for the definition of cover, for any neighborhood of a point, there exists an open. For any point here, there exists open, evenly covered neighborhood. So it lifts disjoint union of homomorphic subspaces, and so we can consider this the image. Which by continuity of my function would be a neighborhood of this point, and since we are so by definition of the product topology, one can always in this neighborhood one can choose a neighborhood, a smaller neighborhood, which will be of the form of the product t times closed interval bt. So even if it's some interior point, we can, even if it's open interval, we can always choose a smaller closed interval. So. Okay, and then from this, so since the interval is compact, so all these neighborhoods they cover, this intervals AT, BT cover interval 0, 1, and since it's a compact space, I can choose a finite cover, finite subcover. And then it follows that there exist some points ti in the interval where I goes from 0 to, let's say, n, so that t0 is 0, and we strictly order it, and tn is 1. So, for example, why does it follow from this? This is because, for example, take ti's to be okay. Let me say how I choose ti, and then I say what is a property which we actually want. Take ti to be endpoints of our integrals. So since we choose, so we had for any t we had some interval, so there was infinite number. Which using compactness, we chose a finite subcover, and in the subcover there will be a finite number of endpoints. So I can choose my t's to be those endpoints, ti's, and but what what is important for me for this kind of for this partition of my interval, looks like this, is that for any I there exists such that there exists n neighborhood of y0 such that for any I f of n times ti plus 1 belongs to U. Let me call it TU some. Let me do UY0, which is open evenly covered. Neighborhood okay, just open evenly covariate subspace of right? So this is because
we can take U to be the we can take N to be the intersection of all NTs for these finite TIs.
well, we take TIs to be just endpoints. So since if you do it like this, any interval, any small interval here, it will be inside some of the intervals
yes,
here.
I'm asking about this N. Can we take it to be
yes,
the
N is the
intersection?
intersection. Yes, exactly. Yes, the S and N is an intersection of T belongs to a finite subcom. So this is if you do it like this, so any NT will be inside N, and this property will be satisfied. Sorry, but okay. Of course, here the choice. Okay, there is. So let me. This becomes too small. Let me make it more clear. So we want. So this belongs to some U, which is labeled by y0 and I. The original. So the original. The choice of the U was depending on y0 and t. So it will be dependent for each interval like this, it will be also dependent on choice of t. And then for each of these kind of intervals, ti plus 1, it also will be dependent on I. So it will be known by y0, comma I. Is it clear? So then, okay. So then we want to show by induction that there exists a lift of F restricted to N, which is some neighborhood of my fixed point y0 times interval starting from 0 and going till t up. So we want to do this by induction. So first, base of induction. I equals 0, 2, because so we can take f tilde 0, right? So since f tilde 0 provides a lift on the whole y times 0, this in particular provides a lift of this restriction n times 0. So then we want to make the induction step. So we want to assume true for n times 0 ti, and we want to show that it's true for this longer interval. Okay, so what's going on? So let me give some picture. Yes. So we have so we choose some y0, some neighborhood n, and so we split it into my interval from 0 to 1 to some small intervals, and so let's see. So this product goes to the action of f. It goes to some point. So let me write it. So let me so this goes somewhere like this, and so let me so let's say this would be image of f of m times ti. This is the image of f m times. Okay, this is I don't actually need this, and so now I want to use the fact that there is exist. So by the property before, which I used before, there exist and evenly cover UI. So let me suppress the y0. Okay. Evenly cover it such that this thing is contained in it, right? So in particular, I mean, we use okay, there was a stronger statement like this. So okay, so let me so this would be the image from. So this was so let me this is the image of this interval times n. This is the whole thing is f of n times the interval, and I can choose some u which contains it, and then by definition of the cover, so P inverse of u. Let me write it y0 I some disjoint union of open subsets in X tilde. So we also know that this thing pi1, let's denote pi inverse, so P inverse of f of what I want y0 times ti. So this is a small point here. So M was the neighborhood of y0, so this will be, so this point is f of y0 ti, and so we so this will be this will be long, of course. So this whole thing, and then so we also know that what. So let me take y0. So let me. What is a good notation? Okay, let me take x. Oh, let me just denote it by f tilde. So we found. Okay, let me back up a little bit. So we found. So we assume that there is a lift. There exists a lift on this interval, so we can use this existing lift of f restricted on this subspace. So we can use it, in particular, we can use it on y0 times ti, right? So we defined the lift of f, which is given by tilde, on this interval times n. And so let it be here. And we know since this is a lift of f, this will also belong to this inverse image of f, right? By the definition of the lift. Right? Because the lift was defined by the diagram like this. It was y times 0 x. But since this is disjoint union, so there exists unique alpha in this disjoint union such that this guy belongs just to one of these subspaces, right? Because it cannot belong to any other, only to a single one, because otherwise it wouldn't be disjoint. So if I denote, so this is some multiple, so you tilde the image of U under the covering, and then there is a unique choice of U tilde alpha y0 I, such that the image of my lift, the image of y0 ti under my lift f tilde is 0. Okay, and so next step is that so we want to define. So we want to make an induction step. We want to define f tilde on restriction of n times this small interval. So if you do this, since we already have a lift here, we will get a lift here, right? If it will be consistent at the point here. And we want to define it as follows. As P inverse restricted on U so let me know P inverse alpha restricted on U, Y0, I. Of F. So where P inverse alpha is a map from U alpha U tilde alpha, so P it's a map from U Y0 I to U inverse alpha Y0 I, right? So because we can define such thing because it's by definition of the evenly covered subspace on each the restriction of P on each U tilde alpha is a homeomorphism. So we can inverse its restriction. We can inverse, right? And of course, this will be self-consistent because the value on Ti will be the same as the value of F tilde, which we defined on this interval from 0 Ti. Well, again, let me mention some subtleties. So here we assumed, that it exists for some n. So before we had so this lift exists for some neighborhood n of y0, and so here when we do the induction step, we choose. So there is a choice of neighborhood here, some neighborhood here, right? So the choice of neighborhood here was actually was depending on I. And what we do, when we do the step, we just replace n by the intersection of n here and n here. So since we always can replace n by a small neighborhood. So let me probably write. So what happens here? So we found some. So there was the lift. This was U. Y0I. So it has some. Its preimage and the pair looks like a joint union of some homomorphic sets. And so we can choose there is unique among them. So that this contains F0 to the Y0I. And so in principle, so the image. This was the image of F tilde under F tilde of n times Ti. But we know that there exists a neighborhood and I times Ti plus 1, such that it contains entirely inside of this open subspace. And this essentially allows us. So you can kind of imagine this. You reconstruct. So once you consider the lift locally construct the lift up to some point, you're sitting on some fixed neighborhood for some neighborhood with respect to for which there is a homomorph P providing homomorphism to the neighborhood here downstairs, and then we continue to construct this false. Questions for this part? So here we proved that the lift exists on for any y0 there exists a lift. So let me formulate it. So since we can go by induction till the end of the interval, there exists a lift of f restricted on n is some neighborhood of y0, and which we denote by f tilde. Okay. So so this was so existence. We show the existence for neighborhoods of any points of any point of f of y. Now we want to show uniqueness, but let me assume here that y is a point. So let me first show uniqueness when y is a point. So y is just a set containing y0. Then show uniqueness by induction. So this is very similar. So first we can show base. So by induction, similar as we had here. So let me show uniqueness on of this lift on y0 times 0 to I by induction with respect to I.
Sorry, but do we require it to be unique over all of y cross I?
Yes. So yes, here. So the statement of the proposition was it's unique. The lift is unique. There is a unique lift on y times I. So let me first prove it for when y is just a point. So base is true since we have fixed f0 tilde. So by the condition of the proposition, we have unique fixed f tilde, which is a restriction of f fixed lift tilde of f restricted on y0 times 0, right? Now the induction step is the following. So again, we assume true for y0 times 0 ti. So what does it mean? For any two lifts f tilde I prime of f restricted on y0 times 0 to I, f tilde must be equal to f tilde prime. So then we want to make an induction step. So again, so choose so here when I write ti, I of course mean I mean this subdivision which was chosen as before. So we know so from the induction assumption, in particular, it follows that f tilde of y0 ti is the same as f tilde prime of f tilde prime of yti. And now we want to show that the same true for, so that those guys, they coincide on y0 times interval from ti to ti plus 1. And this is indeed the case, because well, by the same argument as before, essentially. So since we so we can say that this is this is defined as P inverse of f restricted on y0. And this is indeed the same. Here the by part again to be more careful. This is I use pi minus 1 inverse r, where the alpha is a homomorphism from u y0 I to tilde So this is because, again, since we arrived at this, so if we assume that there is this equality, then so the image to this f, so those values, they belong to the same disjoint here. So again, so if we fix some points, there are some evenly covered neighborhood containing these points in X. So there are some evenly covered neighborhoods. So, but since so we showed that F's coincide at Ti, so the F tilde, the value of F tilde should belong to the same, to the same preimage, to the same connected component of the preimage of the evenly covered neighborhood, because all those guys need to join. Okay, so we showed we showed that there is exists a lift for any neighborhood of a point, and we showed that this, if it's just restricted to a point, it's unique. So now we are ready to finally prove the statement that we want. So this is, we can consider the part 3 of the proof. So, so we defined lifts F tilde and, well, let me know, n y0 to make explicit the dependence on the point y0 and times 0, 1 of F for any y0 and y. And now we use the fact, so since if you take 2 points, y0 and y0 prime, this is a non-empty, then F tilde, so this is if you take first restriction on this guy, and then, so you can say this, the lift on the first neighborhood of y0 agrees with so if you hex, let's say some point y0, y0 prime, this was neighborhood ny0, this was neighborhood ny0 prime. So suppose so we defined lifts for any neighborhood, for any point, for some choice neighborhood. But here the functions agree because they must agree. So if you fix any single point, we show that there is unique lift which agrees with this fixed boundary condition when at the beginning of interval. Because of part 2. And then we can just define, so this tells us that we can, this gives us a well-defined function on the whole y. how did we define this function? So we can take, we take any, we take some point and we take any, so we can use any neighborhood. So any, the definition of f tilde on any neighborhood. And since we show, here we show it doesn't matter which neighborhood we choose, right? So this finally completes this proof, this ugly proof of this nevertheless important property. Any questions? But morally, the idea is that so we have we want to construct lift locally, and locally it's always possible because by this definition of the current base, locally we can always there is like once we choose some preimage, fixed preimage of this evenly covered neighborhood, there is a homomorphism, and we can use it to construct a lift uniquely locally. And then we kind of glue small neighborhoods to get a self-consistent function of the whole space. So let me formulate the first corollary of this proposition is that take path f from 0, which is a definition of from 0, 1 to x, and fix so we take path fix x0 tilde preimage of x0 with respect to cover. Then there exists unique path to the x tilde such that its start point is x tilde and f tilde lifts proof. Take y to be, well, take y to be just a single point in the proposition. All right. Corollary 2 is that let f is a map from square to y be a homotopy, be a plus homotopy between f and f prime plus x, and again fix x tilde in preimage of x tilde x0 where x0 is the start point of both paths, and then there exists unique lift f tilde such that f tilde is a path homotopy between f tilde and f tilde prime, which are lifts. So according to the corollary one, there exists unique lifts of paths f tilde, but now we want to say that any homotopy in between paths in X lifts to a homotopy between paths in X tilde. So this also easily follows from the proposition. So we want to take y to be 0, 1 in the proposition. So first we want to use, so we already showed in the corollary, from the corollary one, it follows there exists unique lift f tilde of f. So let's and we want to also take in the proposition, we want to take f tilde zero, which is a restriction. Take f tilde 0 to be which is a map from 0, 1 times 0 to x to be f tilde. So now we can use the proposition. So we have here y. We have a fixed, and we have a fixed lift. So we have a fixed lift on y times the beginning of the interval to x, which is the lift of the path f tilde. So now we use the proposition. We can use the proposition 1 to say that so we can start there as unique lift tilde. This is my y here, this is my y. Such that it's a restriction on y terms. 0, 1 times 0 is equal to f0 tilde, which is I took to be f tilde, and I can write some picture. So I construct it so let me write this variable here as S. T will be my homotopy parameter. So here I have tilde, and so what remains to show is that my homotopy F tilde provides a homotopy between F tilde and F tilde prime. So I want to show that F tilde restricted on zero one times one is F tilde. Prime, which is a pass. So here it is. So here, sorry, I forgot. I mean, whenever here it's F tilde, of course it maps to F tilde. Okay, so now, so we want so we can view this picture in a bit different way. So let me so first I want to argue that F tilde of t and 0 is equal to x0. So this comes because of uniqueness. So since if I fix my S to be, so I can I want to because this is false uniqueness of the lift of F restricted on T0, which is X, right? So if I restrict, if I consider restriction of F on just the first interval times 0, we know, so since F is a constant, it's just stays to be fixed like 0 because F is a path homotopy. I can always lift a constant map to a constant map, and since it's unique, I must have this, and also the same argument for T. The interval exists as a unique lift and should be equal to F tilde of 1. And then, so what we showed here is that the ends, so all this, this H is mapped to X tilde, and the whole this H must map to F tilde of 1. So this was F tilde of 0. And so we showed that So since this edge is maps to fixed points, it follows that f tilde is a path homotopy. It's not just arbitrary lift, but lift. It's not so I mean, from the proposition, it's obvious. I mean, from the result of proposition, it's obvious that there is unique lift. But we also show that this is not just arbitrary. The lift is not just arbitrary function from square to x tilde, but it's this can be understood as a path homotopy. And this is the condition that this is a path homotopy is that all these edges they map to the same points, which are fixed endpoints of the. Again, you can visualize this picture as follows. So if you have some x, still that here. So if you have some homotopy between paths f and f prime, this is a continuous deformation from one path to another. It lifts to a unique. So it's enough to just fix x0 tilde, which is a preimage, a point in the preimage of P is a covering function. Once we fix f and fixed x0 and we fixed x0 tilde, so we know there is no homotopy, path homotopy here. It gives a unique path homotopy upstairs. Questions? Now we are ready to prove the theorem which we formulated before. Is that phi 1 plus 1 is homomorphic to Z. So let me construct explicitly a map from the fundamental group to Z, which I will denote by alpha, and then I prove that it's homomorphism and has inverse. So let me define a map as follows. So let me first. So of course, if I want explicit construction of phi 1, I want to fix a base point. So 0 is a fixed base point, so fix base point 0 and S1. So remember that S1 we represent as R real line quotient by integers, by integer shifts. So here, okay, to be precise, is equivalence class of 0 in the real line with respect to this quotient. So again, the equivalence relation is that T in R is the same as N. So let me take some path here, and I want to map it to some integer. So how do it? So given a path, I need to tell you what is this integer. So use from the corollary 1, which we just had, it follows that there exists a unique path F tilde in R, which lifts F in S1, right? So since we have a covering map P, which is defined by this quotient, which is the same as a quotient map here, and this is a map F. So we know that this F is actually a loop. So the start and end point are the same. It's given by the projection of 0. It follows that so we have this condition that so P of F tilde should be the same as F. And then follows that P of F tilde P of F tilde 0 is 0, and P of F tilde 1 is also 0. So to have a unique lift, I have to first fix a lift at the beginning of the interval, right? So I fix zero, which is a preimage of this class 0 in the circle. So this was, so let me remind the picture which I had before. So this is a circle, and there is some sort of R, which can be represented as helix. And of course, this the preimage of 0 can be identified with a set of integer numbers inside R. The lift of 0 is a bunch of integer numbers, and so we say so we want to fix so we want to consider the lift of the path such that f of tilde of 0 is fixed to be 0, which is inside the preimage of this bracket to 0. And so this is the condition which we need, so that the path to be unique. And then n, take n to be f tilde f1. So we know, so this will be some integer number because of this property. So this because the covering map acting on f tilde 1 should give 0, which lifts whose preimage is a bunch of integers. Essentially, you can think about it. So if you have some sort of path f here, which winds multiple times, the lifted path would be like this. So you go, and you end up at some. So you start at 0, so you fix a start point, but generically you should end up at some integer number, which projects to the same point here. So this defines so alpha, which,
I have a question. Why are we sure that the preimage of 0 would be the integers?
well, this is because of this of the definition of p, right? So if any so p is a quotient map, right? Or equivalence relation. So if some number equivalent to 0, this means t is integer. Again, since we use some particular representative of this path homotopy equivalence class, so we want to show that this is well defined. Alpha is well defined. Take any other path f prime, which is path homotopic to f. And then, so let's say there is homotopy f between paths f prime and f. And from the corollary 2, it follows that if I find the lifts of f and f prime, they're also homotopic. Particularly the follows that the endpoints of the lift will coincide. It's the same. So the map is indeed well defined, it doesn't depend on the choice of the representative. And so we want also to have it, we want to show that this has inverse. So when we concept map from integers to pi 1 is 1. So given an integer, we want to write some up here and construct some loop here in S1. So let me denote this loop by omega tilde n. So omega n. Where omega n is, so omega n should be a path in S1, which let's say take S, the path parameter, to class of n times S in this quotient. So it's indeed it's a path. So 0 maps to class of 0, which is 0, and 1 maps to class of 1, of n, of integer n, which is also 0. And one can show, so again, we use corollary 1. There exists a unique lift, and one can explicitly corollary 1 and 2. So this unique lift, homotopic to, well, actually, just result. There is this unique lift, omega tilde n, such that this just maps. So I want to, again, I want to have a unique lift. I want to fix my start point. So the lift is a path in R. So it's it's obvious that this is this map lifts this map, right? By definition. And it is inverse. It is indeed inverse to alpha, which was a map from which took to because so let me say this is equal to some number m, because there is because f tilde such that its endpoint is some integer m. Because f tilde and omega m tilde sorry, because so we want to show that because yeah, because f tilde and omega tilde m is homotopy. And I want to make explicit homotopy, so let me denote this by h. So h of s t is s of s times 1 minus t plus t times s. So when t equals, so first of all, it's clear that there's a path homotopy. So the value when s equals 0, this stays to be 0. When s equals 1, this becomes, sorry, m. This becomes m times 1 minus t plus t times m, which is the same as m. And it's continuous, and it's interpolating between f tilde s and s. So from this it follows that indeed the composition of alpha is identity, and the other is identity. final thing we want to show that alpha is a homomorphism, and this follows from the fact that so if I want so I want to show that if I take a composition of omega m, this is not n plus m over alpha. And so to do this,
we need to prove that omega n composition with omega n is the homotopy to omega n plus n.
well, yes, I mean, this is one way to show it. So let's so we need well, this actually this follows from the fact that this is actually not homotopic but just equal. Oh, sorry. Well, no, sorry. No, it's just homotopic. So we can construct so let me, so I don't want to prove it, but let me again use this kind of picture. So we have omega m, and we want to construct some homotopy, like denoted by k, omega m plus m. So how this, so let me explicitly write, so this is a function. So I can understand again as so let me write here R, and let me write here S. So I can represent, let's say, so here I choose a lift. Let me choose a lift of omega tilde n, such as before. So it goes. So here I already construct a composition of paths. So this will be a graph for. So this is the graph of omega n, some lift of omega tilde n and omega tilde n. So let me denote it by omega double tilde n. So this lifts. This is the composition of lifts of omega n to R. So by the definition of the composition, I split the interval.
Sorry, but why do we have two tildes over omega?
Well, because this will be a bit different. So there will be a lift, but it will be not the same lift as I defined before. Because so let me take omega n to be the lift as before. So it will be just a linear function which takes at the end takes value n. And here, what I want to do, so this omega tilde m, I define as the previously defined lift omega n, which starts at 0. And so the previously defined lift, it was the start point was 0 and the end point was n. So I want to define it by shifting this by n. And of course, since this is an integer number, it also defines the lift, right? Because the quotient kills an integer. So this will look like this. So what I did, so I can write, if I write omega tilde n like this, so what I do, omega double tilde, I just lift it by n, and this will be the composition function, I mean the concatenation function. It will look like this, and of course there's I can choose a linear, there's an obvious, I can choose a linear homotopy. Just again use this linear homotopy between this pi-spherical linear function and just a linear function which start from 0 and ends n plus n. Okay, this was the end proof of the fundamental group is of S1 is homomorphic to Z with and it's generated by map, which is generated by the path which takes S from 0, 1 to its closeness, right? So this is indeed true because this in this construction this was mapped to 1 and 1 is the generator.